this computer. All right, so I think it's recording. All right, so let me share my screen and share. You guys have access also to the PDF, right? It's posted there on D2L if you guys want to open that as well. I just updated it today as well because I needed to add some more slides. So that's why you guys can ask questions as we talk, like just normal class. Don't worry. Don't hesitate to ask questions. All right. So casing, well, that's one of the most important part of any drilling, right? And couple of questions that we need to respond is that why we run casing. We talk about the types of casing strings that we have inside the wellbore, their classifications. The wellhead, we don't cover it much really, but we will go directly to the burst, collapse, and tension criteria. These are the three important design criteria that we need to worry about. And all the casing design that we do is based on these three criteria: burst, collapse, and tension, which we will talk about it and how you guys should do that. We do example, and also we talk about the effect of axial tension on collapse strengths. Collapse is a bit more complicated. We have different types of collapse, which we will talk about it later. Examples, of course, we will do a lot of examples, hopefully. If we have enough time, but we do as much as we can. So what is casing? Casing is basically a steel string, steel type of pipe, right, that we run into the wellbore. And once we drill a section of the wellbore using the drill bit, let's say you started from the surface, right? So if you start from the surface, you drill the wellbore using the drill bit up to some specific depths, right? And then you have a wellbore which is not cased. It means that you have a direct connection between the formation that you drill through with your wellbore, right? Then you set casing inside. It's a basically piece of pipe, right, that you run into the system. And once you run that casing, then you inject cement into the wellbore, passing through the casing, and it goes all the way to the annulus. So your annulus would look like here, and here you have all the cement, right? And then you wait until this cement is set for a couple of hours. Once it's set, then you drill again. You continue drilling, and continue drilling means that you will drill through the cement part, and then you continue basically your drilling. So why you run casing? Many reasons. You don't want your hole basically to cave in, right? So if you don't put casing, specifically at shallower depths, you have sands or type of rocks that are not really consolidated. They are unconsolidated formations at shallower depths. So there is a chance that basically those formations cave inside your wellbore, and then you have to clean, and there are other problems that might happen, right? You want to also prevent the contamination of freshwater sands. So usually formation around 1,000 feet or so, there are formations that have fresh water in it, and that they are used for drinking water or, agriculture purposes. So you don't want to contaminate those formation. So what you do is you run the casing, you basically prevent the communication from the formation and the wellbore and anything that is passing through the wellbore, right? So you have drilling fluid inside the wellbore. You don't want that drilling fluid to go into the freshwater zones and contaminate that, right? So you want to run the casing, one barrier, you run the cement, second barrier. So there are two barriers between the formation and your drilling fluid, or later on, once you are producing anything from the reservoir, your hydrocarbon is not in communication with the formations, right? Water migration to producing formation, many other confined production to the wellbore. Again, hydrocarbons, you just want to pass it through the wellbore. You don't want to have a communication with other formation. You want to control pressures during the drilling, which can be done through the basically having the casing inside. And it's basically overall, you can say that the casing is for well integrity. So well integrity means that you have a well bore that is environmentally and also structurally powerful, right? You don't want to you don't want to have a well bore that you will have issues with the both environmental and structural properties. You don't want to have the well bore that basically you have a cave-in problem, or once you are producing oil and gas, you have some formation that might be very permeable, so you will lose your producing oil and gas into those formation, right? So you always want to have that casing in place. Now you have multiple types of the casing, right? Another thing is that that I forgot to mention is that it's basically as you drill down to higher depths, what type of mud do you need? Do you need a higher density mud or lower density as you go deeper? Any idea? Higher density, why?
To control your bottom hole pressure and make sure you don't have leakage from the reservoir into your wellbore.
Exactly. So as you go down, you need higher density fluid because you don't want to have blowout happens or kick happens from formation fluids, right, coming into your wellbore. But if you don't have a casing, what happens? So let's say you have a wellbore, right? At shallower depths, you have formations that their fracturing gradient is smaller, so they might fracture with very low pressure, right? If you are drilling a higher, basically a deep wellbore, and you don't have a casing inside, you want to use a high density fluid, maybe a 14 or 15 pound per gallon. But if that 14 or 15 pound per gallon mud reaches to some shallow depths formation that have a very low fracturing resistance, then that high density fluid might fracture your formation, right? And you will lose all the drilling fluid into those formations. So casing actually helps you here as well. So if you have a casing here, then you don't worry about the drilling fluid density that you are using because the shallower formations are protected from your drilling fluid by using the casing. Make sense? So that's another reason that we do need a casing, right? Any questions so far? Nope. All right. So what type of casing do we have? We have 4 or 5 type of casing that we run usually. We don't run usually this one, the first one, but we start usually with a conductor casing, which we call it. And conductor casing is one of the casings that are used for shallower depths. And again, the reason being that the reason of running a conductor casing is usually that the shallower formations are really unconsolidated, so you will have a lot of sand production when you drill the shallow depths formation, and then you have to clean your drilling fluid and a lot of issues will happen, right? So once you drill, you pass those shallow formation, you want to basically seal those formation. You want to prevent their communication with your drilling fluid and wellbore. So you prevent those issues that caused by unconsolidated formation and cave-in problems, right? So conductor casing can be run. The depth 100 feet to 1600 feet. It's usually high diameter, for 16 to 48 inches, depending on the field that basically they are drilling. And the average kind of size or example is 20 inches, right? So before talking about this, let me show you how the structure look like. So you have basically either a structural casing, which structural casing purpose, which I didn't talk about, it is the main reason is basically to have everything hanged to this system. So it basically hangs the other casings to it. So you have all these casings basically hanged from a high strength material on the surface. So we don't usually run this one, but we usually start from conductor casing, and you drill, right, with a large drill bit. Maybe what if you have a 20-inch conductor casing, what do you think should be your drill bit size? Higher or lower than 20?
Higher.
Higher, right? Because let me delete this one. So it should be, this is the conductor, right? So the drill bit that you are using should be higher than 20 inches because you need to have the casing set inside, and also you need to have some annulus here in order to basically inject cement and fill this area with cement, right? So you run the casing, you inject the cement, cement goes all the way here into the annulus, all the way to the surface most of the time, and then here is called casing seat. That's where the casing is set, right? And then you continue the drilling. You have to change your drill bit, right? You have to do a trip. You use a smaller drill bit size, which is lower than 20 inches, right? And you continue your drilling, and then all the way up to some specific depths. We will talk about these depths and how to set them later on. But then you run the second casing, which is called surface casing. And surface casing, the purpose is usually to protect those freshwater formations because the depths for which those freshwater formations are usually within the setting depths of the surface casing, 2,000 to 4,000 feet. Okay, it might be different depending on the area that you are drilling. For example, in our area last year, we went to the Range Resources drilling pad. Any of you guys were there when we went to the Range Resources last October? No? Yeah. Yeah. So if you remember, basically they talked about they're setting depth casing, and one of the reasons that they set the surface pipe here in this area is that they have those coal mines underground that they are depleted, and they actually took out those formation, and there might be like 20 feet or 30 feet of height that there is nothing there. So if you drill through that, then you will lose all your drilling fluid into those formation underground, which basically their coal are already mined. So they have that issue in this area, and they have to run a casing so they can isolate that coal mine from basically what they are drilling through. So there are aerial and basically field dependent criteria as well for setting these depths, but we will talk about the general criteria later on. And in your project, you have also to design the setting depths of these casing as well. Anyway, so 2,000 to 4,000 feet, the size 858 inches to 20 inches. These are the outer diameter that we are talking about. And an example is the most common basically size is 13 3/8 inch casing. So once you run that, then again, you inject cement, and then once you inject the cement, you have to cement basically both sides, right? Once you drill, and then you run the casing, you inject the cement again. You cement this area for starting from here. And then once the cement is set, then you drill through that cement all the way to the depths that you want to drill. Intermediate casing, inject cement, continue, change the drill bit, and continue. So intermediate string is basically intermediate casing is one of the casings that we usually set because some formations have abnormal pressure. Anybody knows what is a normal pressure gradient? So if you go underground, I think we talked about this probably in the class, right? So if you have water in the formations underground, your pressure increases with some specific rate, right? PSI per feet. That that is called pressure gradient, right? Anybody knows what is the normal pressure gradient that we expect a formation have?
Is it around 0.5?
Kind of close to that number, yes. Depending on the formation, for example, in Louisiana area, the value is 0.465 psi per feet. Depending on the area, it might be a bit higher or lower than this number. But this means that, for example, at 1,000 feet, you expect that that formation have a pressure equal to 0.465 multiplied by 1,000, which is 465 psi. A formation at 5,000 feet, you expect that have a pressure equal to 5,000 multiplied by 0.465, right? So this means that is how much for 0.465 multiplied by 5,000. You expect that at 5,000 you have a pressure of 2,325 psi. But then you realize by some measurements or analysis that, which we will talk about it in a separate chapter later on, that that formation have a pressure of 3,000 psi instead. So this pressure, that 2,325, is called normal pressure gradient, normal pressure. So that's what you expect. 3,000 psi is abnormal pressure. So your formation have an abnormal pressure, right? So you're drilling, you encounter a formation, just a single formation there, that has abnormal pressure. So what you want to do, and then after that you have formations that have normal pressure. So what you want to do, you want to isolate that specific formation, which usually this happens at intermediate depths, right? And in order to isolate that formation, you run intermediate casing, and the depths at which you set those casings is not mentioned, but it's more than 4,000, right? 4,000 to maybe 6,000 feet. You may use multiple intermediate casings as you drill, so it's not just one single string that you use. You might use multiple of these ones, intermediate casing. And then finally you have the production casing. And then production string is basically you have reached to the target formation, and the purpose of the production casing is that it isolates the rest of your wellbore from whatever fluid which is coming into the wellbore. Although the production casing is not the last, what you see here is a production liner, which I will talk about, but production casing also goes all the way. Sorry for my handwriting, it's not, but it goes all the way to the surface. This is called production casing. And then you have a production casing. That means that your formation which have oil and gas are here. That's the setting, basically depths of formation. So it gives you the ability to isolate your fluids, oil and gas, coming out of your reservoir from the rest of your wellbore, other casings, and also give you the ability to run another pipe here, which we call it tubing. And your oil and gas are actually producing from the tubing and not from the production casing. So if you want to change later on your tubing, or doing a repair or anything you want to do later on, production casing gives you that ability to work with your tubing and change it without disturbing other parts of your wellbore, because those pipes have, once oil and gas or other fluids are in contact with them, they may have a corrosion, right? And corrosion means that your pipe will have a problem. You may have a leak later on. So this production casing again isolates your system from oil and gas that is coming out of the wellbore. Any questions so far? Nope. So this is the size. This is the normal size, 7 inches maybe. And liners are another type. Sometimes we use them. Liners don't go all the way to the surface. They are attached to the largest casing that you have used, longest casing that you have used. So if you are having basically intermediate casing as the last casing, if you attach liners, which doesn't go all the way to the surface, then this is called the production liner, right? And production liner again goes all the way to the formation that you have oil and gas. So anybody can tell me why we probably would want to use a production liner? Instead of a production casing. Any idea? Well, if you look at here, you see if you use a production casing, you have to use a lot of pipe, right? Liners are shorter in terms of their length, so they are much cheaper compared to the production casings, right? So being economic, that's one of the reasons that you want to use production liners, right? And other reasons that you don't want to use a liner is that the liners are not as high strength as the production casings, because casings goes to the surface and will be attached to the surface, so they have basically higher strengths and give you more flexibility compared to the liners to work with your basically tubings line. But sometimes if basically you think that nothing will happen, you don't need that much of strength for the formation that you specifically are drilling, then a production liner might be a good idea. All right, so this is it. And there are multiple classification of casings. Outer diameter, that when we talk about, for example, 5.5, 9, 5/8 inch casing, that means that that's the outer diameter of the casing. The wall thickness is another property of the casings. For example, 0.5 inch. We will talk about them later on. Grade of material. So how good is basically your casing? How much is the strength of your casing? That's basically grade of the material. Again, we'll talk about these. Casings also similar to drill pipes. They are not just a single string, right, which is 5,000, 6,000 feet. They are multiple joints that are connected together using couplings. So couplings and threads also another specification of different casings. Range of each joint, that for drill pipe usually we use 30 feet, right? We also have different ranges that we will talk about them, and also the weight of the casing, what weight they have. This is also important for us when we design the casing. We will talk about basically the axial tension, which you guys already know about the axial tension calculations. That comes to the play here as well. So the weight is important for that purpose. So how the casings are basically reported. So there is an API. Do you guys, let me see. Do you guys see this other PDF, or you just see my previous slide?
I see it.
Okay, good. So this is a technical report, equations, calculations, or casing, tubing, line, pipe up, whatever, everything. It's basically American Petroleum Institute report. This is API technical report, and the report number is 5C3. So the way they write it is API R5C3. And in this report, it's all about the casings and tubings. So they talk about different types of casings, what equations you need to use in order to calculate properties of the casing, design the casing, and also at the end of this report, let me see if I can go all the way to the end. Yes. At the end of this report, there are tables that these tables also are available in the book, not exactly as this one. This is the most newest one. The tables in chapter 7 also can be very helpful for you guys. I will share this PDF though with you guys for your project as well. You would need that. But in chapter 7 of your book, if you go there, you will see that there are tables, a lot of tables, multiple pages of tables that talk about different types of casings. So what you will see there is basically a table like this, and in this table the casings are classified into different categories by their size, which is the outer diameter. For example, 4.5-inch casing, right? They talk about others later on, but there is a grade there. The grade is a letter plus a number. For example, J55 or N80. The letter is arbitrary, doesn't have any specific meaning. The number though have a meaning. The number is called the yield strength, the minimum yield strength. And the yield strength of a casing is defined as the tensile strength that is required, tensile stress that is required to produce a specified total elongation per unit length. So when you basically pull the casing, right, when you apply tension to your casing, this casing will basically stretch, right? It basically, the size of the casing, the length of the casing will slightly change depending on how much force you apply to it, right? So the minimum yield strength is the tensile stress that you apply to casing. So you have a specific amount of elongation in the casing. That number is specified by API. I don't remember that number on top of my head. Let me see if I can find it. It's in your book, chapter, again, chapter 7. If you go to chapter 7, let me see if I can find it here. That's chapter 7 of your book. And it's all talk about the casing design. The equations might be very complex, but we will go over them. I just want to find that number. How much elongation should you have for casing? It's good also if you guys want to go and read this chapter. Gives you a lot of information. Yeah, this is here. So this is the definition of the yield strength. Is defined by API as the tensile strength required to produce a total elongation per unit length of 0.005. So if your casing, let's say, is 1 feet, just an example, right? If you have a casing of the size 1 feet, then your casing should be changed by 0.005 feet. And the force that you need to change the size of the casing by 0.005 feet is called the yield strength. Now, different companies report different values of yield strength. So they decided to define a minimum yield strength, means that the casing that you are giving to us should have at least, for example, for K55 or J55, at least should have 55,000 PSI of the yield strength. Okay. Now, yield strength, just be careful. There are stress, which is basically the unit is pressure, and there is a force that the unit is pound, right? So don't confuse. When we say minimum yield stress, we are talking about the pressure, or stress, I should say, not pressure specifically, but stress. Stress means that force per unit area, right? Stress is force per unit area. Now, what is the unit area of your casing? If you basically look at normal to the casing, right? This is the thickness of your casing. this thickness of the casing area, the area of the steel, is the unit area that we are talking about it here, right? So the force that you need to apply to that casing in order to change its length or relative length by 0.005 feet is called the minimum. It's called the yield strength, right? Now, the minimum yield strength, some companies may produce a casing that have, let's say, 56,000 PSI. They will categorize it into J55 because that casing have a minimum yield strength of 55,000, at least 55,000 PSI strength. Does it make sense? Any questions here? All right, so anyway, in that table, you will see that minimum yield strength. So if you look at here, J55 means that you have 55,000 minimum yield strength. We will use this number later on when we design the casing. So some others, I think in the book as well, there is also a column that just gives you that number as well. So for example, for J55 is 55,000, C75 is 75,000, 80 is 80,000, and that's what it is. Now this number is usually higher than the elastic limit of your casing. Anybody knows what is elastic limit? What does elastic limit means? You guys have strengths of material, right?
Yeah.
All right, so what does elastic limit means when we talk about basically deformation of the casing?
It means the limit before it will no longer return to the original.
Exactly. So if it can return, which means that it is within the elastic limit, there is a linear relationship between that stress and that relative elongation of the casing based on the force that you put. Anybody knows what do we call that epsilon? So this is called the stress, right? And this is called strain, exactly. So this is called the strain. And the definition of a strain is that delta L over L, change in length over original length, right? So you apply 55,000 PSI, that casing will have a relative length change, which means the strain of 0.005. So that 0.005 that I was referring to is actually strain, right? So how much change in length per the original length of the casing, right? So usually this minimum yield strength is above the elastic limit. So it's in the, anybody knows what is after elastic? What do we call it? Plastic, right? So this is elastic, the red part, right? And the green line here is called plastic limit. It means that if you apply that force to the casing, then the original length of the casing, you cannot return back to that original. You had a permanent deformation of your pipe. So that's what it means, okay? Now, there is ultimate strength as well. That means that if you apply a force more than this, then your pipe will break completely, right? So you shouldn't apply more than that. Of course, when we design the casing, we only care about this number because we want to design for the worst case scenario. So if we don't want to pass these values in the minimum yield strength. So we don't want to apply a tensile strength at least, or a collapse, which we will talk about, or a burst, which we will talk about again, stress on the pipe that is more than these numbers for the specific grade that we are designing later on. Okay, so the minimum yield strength is shown with YP as well. That's the symbol that we use. And also ultimate strength is UP. We don't use this in our equations, but we use the minimum yield strengths. So again, the reason that we call it minimum is because different companies produce different types of pipes. Some of them may have 41,000, some of them might be 42,000, some of them might be 43,000, but we don't have a specific number in the tables for them, in the standard tables. So they will categorize into 40,000 psi. So they will have a minimum yield strength of 40,000. All right, any questions? Well, that's one basically criteria. That's the grade of material of the casing, the wall thickness, the outer diameter. They are there. Let me see if we can see. So outer diameter, grade of the casing, right? Inner diameter, wall thickness, all these information are also in this tables that you will go later on. You will use it a lot when you design your casings. So the weight of the casing, of course, is a parameter, which I should see it somewhere here. Where is the weight? Probably that's not the complete table. That I need to refer to. Don't worry, I have the full table, which I will share it with you, and it has everything in it. So you will see that the weight is also listed here. I think I have examples here as well. Range of the casing, there are 3 ranges, 16 to 25 feet, 25 to 34 feet, and greater than 34 feet. So these are the ranges of the size of the casings. So of course, when a company creates a casing, doesn't have a specific length. For example, if they make a range 1 casing, right? That means that in range 1, 95% of the pipe must have a length of 18 feet or larger. That's how they, so not all the casings have exactly the same size as the companies manufacture them. So there are some basically variation in lengths, but when they give it to you, they will tell you that, okay, based on whatever casing that we give you, this is a range 1, and 95% of our casings have a size of 18 feet or larger. I have the numbers here. So for range 2, 28 feet is 95% of the casing should be larger than 28 feet. And for range 3, 36 feet is basically 95% of the casings that they give you. 95% of the joints of the casings that they give you should have a length of 36 feet or larger. So that's basically kind of the standard size of those casings. All right, so now these casings will couple together, right, using API threads. If we have time, we'll go over them probably because that's part of the design as well. So we'll see how it goes. There are different types of casing threads and couplings, which we will talk about them later on, but these are the names just here. You can check the book as well. There is a exact definition of these terms: buttress, extreme line, API round, thread, long, short. Probably we'll talk about them, but at this point, we're just gonna skip it. All right, so let me skip this slide and we talk about the normal pressure gradient, right? So this is pressure. This is, this is depth. This is pressure. If you are in normal pressure gradient, then you follow this linear line. If you are basically not going through that linear line, then you have abnormal pressure. And this pressure gradient, these are the formation pressure gradients, right? These will be used later on when we design the basically the depths of the casing that we are setting in the wellbore. Okay, so we'll talk about this later on, but just know what is the definition of normal pressure gradient and what is the definition of abnormal pore pressure gradient. Examples of basically casings again here. What we do in the design, as we talk about it later on as well, is we start from the bottom. So let's say you just want to design. So each casing type will be treated differently. The intermediate differently, surface differently, production differently. Each of those casing, we design them separately. And when we design those casings, we start from the very bottom. What do you guys, what do you think is are the most important criteria for designing a casing? I mean, what should we have on mind when we design a casing? What criteria you guys think are important?
I'm assuming economics is probably the highest one.
Economics is very important, but what else? I mean, economic, definitely, that's a great point, which we will talk about it later on as well. In addition to economic, what else should we consider?
Leakage or anything like that, would it be? Or pressure, so that it can handle the pressure.
Okay. Somebody else also said something.
Said the underground pressure.
The pressure that, so well, yeah, pressure. So you are hanging these casings from the surface, right? So, and then these casings have a length, right? And then they have a weight. And then you are putting a axial tension on the surface, right? The question is that, does that casing can handle that axial force, right? So that's one of the properties which is called tension criteria, right? So there are three main design criteria: tension, collapse, and burst, which we will talk about them. But besides these three, economic is also important, right? So when you design a casing, you just don't look at that your casing have the best basically properties of strength. You also need to look at the economy. If that was the case, then everybody would go and just choose the highest grade, best material casing for the whole system, right? And there is no design then, right? It can handle any situation. But that's not the way we do it. So we need to consider the economics. We need to use the cheapest possible casing that can handle the worst case scenarios that happen inside the wellbore. That's what we want to do. Okay. And for that purpose, we start from the bottom, the very bottom. So for example, in your wellbore, you might have a section. Let's say you are designing your production casing. This might be I don't know, J55 casing with one specific diameter. Then from here to here, you might use, I don't know, K80 casing, right? And then from here to the surface, you might use another casing, let's say P110 casing. You see that I am increasing the strength of my casing, because as you go up, you will see later on that your casing should be more have a high strength, because it basically the more tension forces are applied to those casings. It also depends, but usually that's the way it is. Anyway, so you might use different grades of the casing just for your production, right? So 100 joints of, I don't know, P100, 50 joints of K80, 10 joints of J55 casing. And that is what you want to do. You want to find those numbers. What type of casing, what grade, and what lengths for these casings should you use. Before doing all these things, you would need to decide about the setting depths of this casing. That's a different story. Okay, so we'll get back to the setting depths later on. We will first try to cover designing a single string of casing. As you know the depths of the casing and everything, you already have those information, you assume, you design it, right? And then later on, when you learn how to design a single string of the casing, then you will learn what depths should you set different types of casings. And then you'll be able to do your project, okay? Any questions?
So I got a question
Sure.
on J55.
Mhm.
So like all you only care about like the minimal like attention like the
Yield strengths.
55, yeah.
Yeah. So yeah, when we design the casing, that's not the only thing that we care about. You will see if you design tension, for example, you care about some other numbers such as where is that number? Should be in the next. So you see, for example, for collapse, you have a separate number for each casing, right? Each grade, they might be, you might have two, let's say 3 NAD casings, but all of those NAD casings have different properties. Some of them have higher collapse resistance because their thickness are different, you see, right? And they might have different values of tension strengths. They might have a different values of burst, basically resistance. So we don't just look at the number here. We also look at other criteria such as their collapse resistance, their burst basically value of how much burst pressure they can sustain, and also how much is their body internal. This is basically your burst, which we will talk about it later on. You will learn about that. But yeah, that's not the only thing that we look at. We will look at other properties as well. You will learn about that as we go. Any other questions? So we'll not start basically the design today because we are almost done for this session. If you guys have any question, please ask. Starting basically next session, we actually start to talk about design, which are design criteria, which are tension, burst, collapse, and how to design a casing based on these properties. Any questions? Nope. All right. So if there is no question, I'm gonna stop this recording.